So here's another example. This is a really important one. It's really important to know the relationship between these two. So what we want to do is, in an asymptotic sense, sort of in a big O sense, we want to compare log n with the square root of n, right? And understand which one of these grows faster. We know they both look similar. So, if you sit down in PyPlot or something like that, or Excel or whatever you like, and plot them, the log n looks like this. So this is log. Square root looks like this. Log n square root of n looks like this. And so they both have this, this concave shape, and it's not clear just from the first couple points which one is going to grow faster. So how can we check? We can just run them through a limit test, right? As simple as that. So we can just compute the following. We can compute the limit, and I'm going to put log on the top, the limit as n approaches infinity of log base 2 of n divided by the square root of n. Okay. So now what is this? This is a beautiful candidate for L'Hopital's rule. There's no other obvious way to simplify this, right? So we should try to use L'Hopital's rule to get at the answer here. Why is it a candidate for L'Hopital's rule? Well, because both of these go up to infinity as they get very large, right? Eventually, these are both unbounded. They don't just level off. They don't get to infinity very fast, but they do both go to infinity. So because we have an infinity over infinity situation, infinity over infinity, this means L'Hopital's rule. So what do we do with L'Hopital's rule? Let me scroll that stuff out of the way and just focus on the math. So with L'Hopital's rule, we take the derivatives of the top and the bottom. So this is going to be equal to, and here let me just put L'Hop so that you can see what we're doing. So this will be equal to the limit as n approaches infinity of the derivative of log 2n, derivative, divided by the derivative of the square root of n. Okay, and so you got to go back to your derivatives tables and remind yourself what these things actually are. But these are the functions, and so I will just provide them to you here, but make sure that you have some easy access to these actual functions. So first, this is the log base 2 of e of 1 over n. Okay, so that's just a constant, log base 2 of e, times 1 over n is the derivative of log base 2 of n. And then the derivative of the square root of n is 1 divided by 2 times the square root of n. Okay, so now we still have some kind of a weird expression, but maybe we can manipulate it in some way to make this work nicer. All right, so let's chase this stuff through, find some constants. Right, so log base 2 of e is a constant, 1/2 is a constant, and we're dividing by it, so the 2 pops up, we pull the whole thing out of the limit, and the constant outside of the limit looks like this. 2 times log base 2 of e, now times the limit, right? And so this is just a constant. We're mostly going to forget about it, because constants don't really make a difference here. So times the limit. Now what do we have? We have a fraction. So notice that our fraction over here had 1 divided by n divided by 1 divided by the square root of n. So we throw the square root on top, have the n on the bottom. This is basic algebra 1/2 stuff or whatever back in 8th grade. So this is divided by n, right? And so now what do we got? We still have this silly constant out front, log 2 of e times the limit as n approaches infinity. And now how does this thing evaluate? Well, the square root of n divided by n is equal to 1 divided by the square root of n, right? So you can think of this piece, you can think of n as equal to the square root of n times the square root of n, right? And so I've got 2 square roots of n on the bottom, one of them cancels with the top, and what I'm left with is just 1 over the square root of n. And what does this evaluate to? It evaluates to 0. Because I've got something on the bottom that goes to infinity as n approaches infinity. Okay, so this whole thing evaluates to 0, and sure enough, that constant doesn't matter at all. So it doesn't even matter if I missed one of the weird log e things, right? It just goes away. So it evaluates to 0. So what does this mean? Well, it means that these have a different order of growth. So 1, it means that log 2 of n is not big theta of square root of n, right? And then what's the other piece that it means? It means that log base 2 of n is big O of square root of n. Is big O of square root of n. Okay, and so you should just memorize those two statements right there. Those are actually really important, the bottom one in particular. But now you know how to derive it for yourself, right? So if you ever forget whether or not log grows faster than square root, now you can derive it for yourself. So let's do another similar one. So it's similar in the following sense. Square root and log are both nice slow growing functions. And it can be hard to remember sometimes which one is which. So now let's look at two fast growing functions. So let's do example 3. And we'll compare 2 to the power of n with n factorial. So we'll compare 2 to the power of n with n factorial. So to be consistent with my notes, I just want to make sure that I have the right thing on the top and the bottom. So here's how I'm going to do this. I'm going to compare the limit of n factorial divided by 2 to the n as n approaches infinity. So this is the situation where Stirling's formula comes in handy, right? This is what Stirling's formula was made for. So I'll say this is the limit as n approaches infinity of now Stirling's formula plugged in here. So Stirling's formula is, and I'm reading off my notes because I don't have this memorized, shocker, 2 pi n times n over e to the power of n, all divided by 2 to the power of n. Okay, so let's get rid of some constants, shall we? Just to make this handy. So I will pull this constant out. So let's make this 2 pi, square root of 2 pi, times the limit as n approaches infinity. Now I've still got that square root of n left in there, and then all of this junk. All right, so what do I do with that junk? Well, notice this junk is something to the power of n divided by something to the power of n. So I can just mash them together, and it's all still something to the power of n. Right? So what do I have? I've got n divided by 2e all to the power of n. Okay. So what do we have here? What are we looking at? Well, we're looking at n square root, right, which goes off to infinity. And we're looking at something in here, right, in the parentheses, something that goes off to infinity, right? So certainly n over 2e, that goes to infinity. And then we're raising this thing that goes to infinity to the nth power. And n by itself also goes to infinity, right? So we have a whole bunch of stuff that's going to infinity and nothing to slow it down. There's no longer anything that's growing fast in the denominator here. So take it all together, and this whole thing, the constant goes away, the square root goes away, all these powers go away, and we just say this whole thing goes to infinity, right? And you can check that it all goes to infinity by looking at each of the component parts. All right, so if it goes to infinity, what's this mean? Well, this means that n factorial is not big theta of 2 to the n. And then it also means that n factorial is big omega of 2 to the n. Of 2 to the n, right? Which means that n factorial runs away from 2 to the n. Factorial growth is much faster than exponential growth. And there we have it.